Hi, my name is Eric Van Hensbergen. I'm a fellow in ARM Research here in Austin, Texas, and I'm excited to talk to you today about our experiences deploying Kubernetes at the edge in a project that we call Smarter. For those of you that don't know ARM, we design the IP that goes into billions of devices, from microcontrollers the size of a grain of sand to the #1 top supercomputer in the world. We're on a trajectory to seeing 1 trillion devices in the world interconnected, and these devices need to be managed and they need to have software developed for them. And so we're very interested in creating platforms that allow you to securely develop and deploy software through the entire spectrum of these devices. And part of this project is about that. But ARM is also really passionate about sustainability, and part of our corporate mission statement includes our responsibility in helping to achieve global goals. And these span the spectrum from trying to eliminate poverty and hunger, to trying to be better stewards of the environment, to try and build more sustainable cities and communities. And a lot of this project, our initial focus has been in use cases around smarter cities in support of several of these global goals. The world population is exploding, has been for some time now, and the trend just continues to tick upwards. And the population in our cities is similarly exploding, but at an even greater rate as folks move from more rural areas into urban areas. And this creates a lot of strain and stress on that urban infrastructure. Cities already consume 75% of the global energy resources and account for 80% of the emissions. There are also major trouble spots for water, where tons of clean water is lost every year due to leakage and other mismanagement. And those aren't the only resources that are involved. So a smart city should be about the effective integration of physical, digital, and human systems to build a more efficient environment in order to create a sustainable world. And that's what we wanted to focus on in this project. The goals, the outcome of this is tons of additional efficiencies and, frankly, just time back for people, time that they don't have to spend sitting in traffic, better healthcare, better public safety, more efficient cities that don't have to raise higher tax rates, better education, and so forth. So there's a ton of good reasons to deploy smart city technology. And now it's a question of how do we create this technology so that it's actually usable by people to benefit people. In this project, we chose to partner with colleagues at Argonne National Labs and academic collaborators at Northwestern and the University of Chicago that have actually had a Smarter Cities project going since 2014. They've deployed hundreds of nodes around the city of Chicago and have pilot projects all over the world. These nodes are really interesting in that instead of being a specific sensor or a specific application, what the team did in the Array of Things project was create a platform that contained lots of different types of sensors, including multi-use sensors like cameras and microphones. And then they bundled them together with intelligence in the form of ARM-based processors that were connected to a network. And that allowed them to not just collect data, but be able to analyze that data on the nodes. This gives a lot of additional efficiencies in terms of the cost of their communication, as well as providing additional privacy and security guarantees, since the data, like video or audio, doesn't leave the node and is processed locally by machine learning algorithms running on the node. And they have a whole host of applications that have already been built for this platform. Things like counting cars that are passing the sensor, pedestrian counting, identifying wildlife, early detection of wildfire, spotting drones, spotting flooding, and even being able to do agricultural analysis based on images from the camera. So there's a ton of these different applications that they built in place. Their whole stack was open source, so it was really interesting. And in talking with them, they are embarking on an even more challenging project, which is taking that base infrastructure, expanding it to even more collaborators to do wider scale environmental monitoring, climate monitoring, and so forth. And so, but in this new environment, where there'd be many, many more collaborators and many, many more applications, they needed a better solution for how they were going to manage the applications running on the edge. And so we started talking with them about using cloud native technologies, and Kubernetes in particular, as a way of managing their applications. Since their applications were mostly open source, we kind of dove in and downloaded their application, started the process of containerizing them, and trying to deploy them with Kubernetes. And we had really good results and evolved that project over time, and that's what I'm going to take you through here today. So we started off by building our own version of their nodes, which included an edge gateway with network connectivity, a sky-facing camera and a street-facing camera, as well as weather and environmental sensors. And then we built a software stack on top of something we call Project Cassini at ARM. Project Cassini is really not just a software stack, but a set of platform standards that makes it easier to build an entire ecosystem for the edge. It starts with ARM System Ready, which is all about standards for running standard operating systems and virtualization solutions on these embedded boards. And so we've created this set of specifications that if the hardware platform meets these specifications, they can run a whole host of standard operating systems from standard vendors, as opposed to requiring some specialized embedded software. Another area of standards activity within Project Cassini is around security. And one of the big areas here is a project called Parsec, which provides a PSA certified security solution with a standard API layer, no matter what the underlying hardware security supports. And this is also an open source project. It's something that is being incubated in the Cloud Native Computing Foundation, and we use that as an integral part of the security that we deploy in Smarter as a way of protecting credentials, verifying software updates, protecting communication, and verifying applications. So that's another major component that's part of Project Cassini. And then, of course, the other component itself is the use of cloud-native stacks in this ecosystem. So Project Cassini just had its big rollout in October 2020 at our developer conference, and I encourage you to go read more about it at arm.com/Project Cassini. Included there are blueprints for all sorts of different solutions in industrial IoT, smarter cities, automation, and other areas. So I encourage you to go and look at that. Focusing a little bit on the cloud native for the edge piece, when we kicked off this collaboration with Chicago, we started by saying, what in the existing cloud native world could we take advantage of in terms of methodologies, ecosystems, APIs, and tool chains that we could deploy on the edge? And so, of course, we looked at things like Docker and Kubernetes and Rancher as a good starting point for how we might approach this edge deployment. And then we combined that with server-style modern application management techniques, including continuous integration and deployment, using services like GitLab to manage all of that, as well as application version control, and then looked at where were the gaps in those technology stacks that work really well on the cloud that may not work as well at the edge, and then developed a set of extensions and extended methodologies that then match these cloud native technologies more to the edge. So what's different on the edge? Security is different on the edge. There are many more attack vectors in edge-based environments. Your nodes aren't sitting in a locked cage in a locked data center. They're distributed on light poles and attached to trees and in all manner of different places. So physical attacks become a lot more likely. So it's much more important that you have really robust security and encryption baked into the hardware, that you have secure boot verification so that someone can't replace the operating system and get access to your data or compromise your node, and so forth. And so the other thing that's quite different on the edge is how you approach multi-tenancy. In the data center, you've got these big iron servers with lots of memory, lots of storage, and lots of network. At the edge, you have none of those things. You've got much more constrained compute power, you've got much more constrained storage, much more constrained memory, and your network bandwidth may be limited, unreliable, and metered, so that you really want to constrain how much you rely on the network for interacting with these devices. This constrained node environment also impacts how you deploy applications, how you think about constructing applications in order to optimize for the resources that are there. And that different connectivity model isn't just about network unreliability or metered connections. It's also about the security model that you may want to have on the edge. You're not in a data center where everything's tightly coupled on the network backplane. You're across LoRa radio links or cellular connections or Wi-Fi Ethernet, and those create very different environments for how you want to interact with things. You don't have this flat network topology. You may have all sorts of NATs and firewalls and gateways that prevent nodes from talking to each other, or even from managers to be able to directly contacting the nodes. finally, you actually have physical devices that you need to make a lot of use of in the form of the sensors. I've got cameras, I've got microphones, I've got weather sensors, I've got environmental sensors. None of those things are typically available in the data center. And so we need to handle extending Kubernetes and these cloud native mechanisms to be able to manage the physical devices, and also to potentially share access to the physical devices themselves or the data that they're producing, and wrap policies around how you manage those devices if they have some sort of a control path. So for example, changing the focus on a camera or a direction on a gimbal or an attenuation on a sensor. So how do you wrap policy around who gets to make those changes in a multi-tenant environment? Kubernetes works really well in the cloud for managing applications. But on the edge, it's a little bit different. In the cloud-based environments, you deploy pods, you deploy services, you deploy replica sets, and you don't really care where it runs necessarily. Maybe you care within a certain regional zone, but more or less, you just say, I want this service to be available, and maybe it's connected to an IP address. But in the edge, it's a little bit different. You really want to deploy an application across a huge set of nodes, not just have a few replica sets for load balancing or for redundancy. If I want to run an ML application connected to a camera that's doing pedestrian counting, I may want to run that on every node that has a camera. And so the way that we approached this was, instead of drastically modifying Kubernetes, we worked with existing Kubernetes mechanisms. So most of our applications are deployed as a daemon set, which by default gets run on every node in the cluster. And what we use is a node selector within the daemon set that uses labels. And that allows us to label different types of nodes to be able to run different types of applications, including running multiple applications on a node just by assigning multiple labels to them. So that's the foundation for how we use Kubernetes for our edge-based deployments in smarter cities, because all of the use cases we had, while there'd be several tenants and several sets of applications, in most cases, what folks wanted to do was deploy their application on every node, and daemon sets gave us a really convenient way of doing that using Kubernetes. I mentioned about the different connectivity environments on the edge. One of the things that we set up in our initial version was a networking model where the edge node could contact the manager, which is sitting in the cloud, but the manager couldn't contact the edge node, and the edge nodes couldn't contact each other. There were a variety of reasons for this, but the main one was a security consideration, as well as simplifying dealing with the fact that we might be dealing with all sorts of environments with firewalls and NATs and other things that would make it difficult for the edge-based nodes to be contacted from a central authority. In order to support that sort of environment, one of the things that we did was we changed the networking model for the container networking model we were using a little bit to try and make the nodes a little bit more self-sufficient. So the default mode of operation is that containers running within a node are only talking to other containers within the node or public internet services. And so within our container networking is kind of node per node, and there's no ability to reach node to node through Kubernetes using our existing container environment. This also allows us to create a node local DNS, which helps improve reliability for when we're running with an unstable or disconnected network, as well as improve performance just by able to use the local DNS resolution to find my local services and not having to always go to the cloud to find it. It is set up hierarchically, so you can still use cloud-based DNS services as well, but the default model of operation is that everything sits within the node. We have been working on extending this recently with options for being able to have bidirectional communication by using tunneling, both from the cloud to the node as well as across nodes, so that we can have richer environments if you want to have applications that operate amongst peers more directly. But our initial set of use cases didn't have that, so we went for this much more constrained environment that's much easier to deploy in difficult networking environments. I talked a little bit before about physical node management. There's sort of two layers to this in what we've done. The first thing that we've done is we have a device manager that runs alongside Kubernetes and informs Kubernetes about the physical devices on the node that are available for containers to use. It also has information like whether or not that particular resource can be used by multiple containers at the same time. certain environments don't lend themselves to sharing easily in Kubernetes. So something like a camera, or a microphone. And so one of the other things that we have is we have containers that provide multiplexing services for those devices, where the physical device will be associated with the multiplexing container, and that multiplexing container can serve that data as a service to multiple containers. And that's currently the way that we're dealing with video and audio. In the case of audio, we're just using Pulse Audio, running that within a container, and offering network service within the Kubernetes cluster to be able to access those audio services. And we have a similar sort of setup with GStreamer now for video access. The other physical device that ends up being quite interesting in how you share it are forms of accelerators. So within the cloud, AI accelerators like GPUs and TPUs have built-in support for multi-tenancy. But in embedded devices, the embedded form of GPUs and the embedded form of TPUs and other ML accelerators don't have good built-in support for multi-tenancy. And so we looked at a number of solutions for how we would be able to share an accelerator like the GPU on a Nvdia Xavier amongst multiple applications. And there are a few different options here. We looked at TensorFlow serving. We looked at Redis AI. But what we settled on in our current example applications is to use a service called Triton, which was open sourced by Nvdia. And Triton sits on top of the GPU and provides sort of a inference as a service server that can then be used by multiple applications. It manages your ML models and then multiplexes requests from multiple applications to that set of ML models and then returns the result. And so this ended up being sort of a perfect solution for us, whereas previously we could only have one application that could run one ML model on the system and not having access to the GPU. Triton gave us this ability to multiplex that a little bit more. And that became even more important when we started talking to a couple of our partners that were deploying systems, and what they really wanted was a fully virtualized environment where each tenant saw a private version of each physical node, each physical set of sensors and pods in the internet. And so what we did to accomplish that was we actually ran multiple Kubernetes. So we'd run a node level Kubernetes that then could deploy containers with their own K3S client in it to provide a per tenant Kubernetes view into that client. And then they would share some of these physical node resources like GPUs or sensors using top-level services managed by the node-level Kubernetes client. And so that gave an interesting solution for how you can even provide private views and private partitions within each of these physical sensor nodes. And so another thing that we did is look at extending the Kubernetes dashboard for more rich support of labeling environments, including geographic labels and map-based labels, because labels were such a critical mechanism for us in how we deployed software. And so in addition to these sort of very generic sort of label manipulation extensions that we made to the Kubernetes dashboard, we also layered on top of that sort of an app store / application deployment mechanism that makes it very easy to deploy applications to a geographic area or to a set of nodes and a logical hierarchy of nodes in support of the project. So what we've ended up with at the current point of time is what we're calling V1.0 of Smarter, which is still in testing and final sort of tuning, but I expect it to come out later this month. Everything's already available as open source, and so you can get access to our earlier releases or see our current bleeding edge, which this diagram sort of represents. Our Kubernetes solution is built on top of Rancher's K3S, so we run that on every node, and sometimes, as I mentioned, we run several instances of it on every node. We've slightly modified it in a few ways in order to better fit some aspects of our environment, but more or less it's a stock K3S. And it and Pelion, which is our ARM's management service for how we do over-the-air updates for the operating system on the nodes, sit on top of Parsec, which is that security interface that I mentioned earlier. That's part of the Cassini Foundation. And then that K3S manages pretty much everything else that's running on the system. And we have sort of different ways to support the multi-tenancy. You can either just support it in a flat Kubernetes way by just allowing multiple tenants to deploy daemon sets to the node that use this common set of node services. And in addition to some of the ones I mentioned earlier, we're running FluentBit with MQTT as sort of our data plane for the nodes. So that acts as a service for ways applications can communicate with each other, as well as an uplink for data from the applications to cloud-based repositories for visualization or further processing. So those can run on top of Containerd or Docker, whichever you choose. The whole system's built out of modular components, so people are free to use whichever services they want or replace them with preferred services. But if you want that private node view per tenant, you can run with our hierarchical K3S, which basically just uses Docker on Docker, or Docker in Docker to run private K3S servers from the main node level K3S server, as I described earlier. Or you can run on top of Kata containers. And that can be used to just run container partitions in a flat model, or you can use it to run the private K3S in this brokerage multi-level model. And that what Kata containers buy you is by wrapping the container isolation in a virtual machine, it gives you an even higher level of isolation and security out of the environment. And so that's why that's beneficial. On the server side, we've got a bunch of different things that we either have or are developing, including sort of example reference CI/CD flows. We've got example setups with using InfluxDB to store data from the nodes and then visualizing it with Grafana. And we're working on a bunch of additional services around supporting sort of a community ecosystem of applications, as well as cluster-wide sort of goal-directed orchestration and better management of machine learning models. So just kind of an example of an output from a set of nodes. So this is, you can kind of see here a Grafana visualization. There's a node map where you can select different nodes to get data from them. These nodes have temperature sensors, air quality sensors. They also have the cameras. So in this case, the node's running a pedestrian counter and a car counter. So you can see over time as people walk by, you can count the number of pedestrians or count the number of cars. And so forth. And so this is just sort of a nice little visualization, standard cloud native visualization wrapped around the way that we run the servers, including a bunch of telemetry from the servers on how they're running, what their CPU utilization is, and so forth. So now that we kind of have this foundation in place, there's a few different things that we're looking at going forward. One of the things that we've kind of identified on these constrained devices is sharing streaming data like video may not be the most efficient in our current examples. And so we're looking at different models and how we better share streaming data and how we better hook that into pipelines of AI inference engines without creating lots of unnecessary copies and memory traffic. Another area that we're really interested in pursuing is doing more with not treating the nodes as a set of separate entities, but looking at how we distribute applications across nodes so that the applications can coordinate with each other. So for example, if you're looking for a lost child and he's moving from camera to camera, the cameras can kind of coordinate to pick up finding that child or lost puppy instead of having to do it from scratch. The other thing that we're looking at from a distributed systems perspective is leveraging the fact that we have varying loads across these different devices depending on what's happening, and trying to figure out how we might, if we need to, how we might leverage some of the compute or accelerator resource from a peer node if the current node is overloaded due to the current situation. And these same sort of things can be used to add reliability to the network environment in these wireless environments that may have sketchy long-range communication but might have better short-range communication. And finally, a big area on the hardware side we're looking at from a co-design perspective is what is the right model for multi-tenancy for AI accelerators in these constrained environments, and how do we get those features built into these embedded systems. ultimately what we're working towards is a fabric that's easy to deploy applications from the top down, from management nodes out to a whole host of nodes. But the other thing we're really interested is in bottom up. So if I'm walking through my city, is there a way that I can leverage the compute that's all around me to maybe offload something running on my cell phone, or if I'm wearing augmented reality goggles, or if I'm driving my autonomous car and I want to be able to leverage the extra sensors that are up on the street poles to give me a better view of what's over a hill or what's coming at a blind intersection. So all of this is lots of good opportunity, lots of hard distributed systems problems, lots of hard security problems, and that's sort of the current focus of our ongoing research. Another area that we're spending some time looking at is improving the tooling around software development and deployment. In particular, all of these different models running on the node, you may not know beforehand what other AI models are on the node. And so figuring out how we characterize these models beforehand to know that they're going to fit if we decide to deploy them, or also maybe auto-generating several different versions of the application or model to fit in different resource constraints, or to be optimized for different hardware, because the hardware at the edge is very heterogeneous. You don't know whether or not you're going to have accelerator, you don't know how many cores you have, you don't know how much memory you have, and we want the same applications to be able to run across all of that. So building up tooling to allow applications to adapt to the environment is sort of an interesting challenge. And one of the ways that we're looking at that as well, everything we've done to date has been container-based, but in looking at the applications we've been running, we see a lot of applicability of serverless or function as a service technology for crafting those applications, and we feel like it may be a much more efficient model for deploying these applications to the edge, particularly in combination with things like inference as a service and Triton. So we've done some proof of concept work around deploying serverless to the edge. We had an OpenFaaS example that runs on our existing Smarter Stack, but what we saw was a lot of opportunity to specialize that for the edge. And so we're kicking off a project now to look at how we approach that and rethink some of the different models for how we might isolate things in a serverless environment on the edge, and how we might optimize both the hardware and software stack for executing those serverless functions as our primary model. So this is an open reference design. You can get access to the source code as well as example images through our getsmarter.io, which can lead you to our GitLab site where everything's stored. That also includes a bunch of documentation, blog entries, and other examples that you can walk through. And so I encourage you to go look at that. If you're interested in the Chicago work, you can go to their Array of Things site. There's a link on the slide to learn more about Array of Things and their Waggle platform and Sage. And we're continuing to work with them and explore how we integrate some of the stuff that we've developed into their next generation. There was a link earlier on Project Cassini, but you can also get to it through a link in the slides if you're interested in learning more about ARM's edge standards and reference blueprints. And there's also a link here to ARM Pelion Edge, which is the management solution that we're using to deal with over-the-air updates as well as managing nodes in the field. Everything about Smarter is open source. It's all modular, so we look forward to seeing how people use it and how they combine it with their own solutions and how they extend it. So please check it out, collaborate with us. It runs pretty much everywhere K3S runs. We have pre-built images that run on Nvdia Xavier AGX, Nvdia Xavier NX, as well as Raspberry Pi 4. But we've had folks run it on Nanos, on Rockchip-based platforms, on x86. So there's a ton of different options to go off and play with it. Also, in our GitLab site, there's a full set of example applications, ones that we ingested from the Argonne work, including pedestrian counting, audio classification, car counting, weather monitoring, and full instructions for how you can set all of that up and build your own Smarter City sensor network that you can then extend in all sorts of different and useful ways. So thank you very much for your time, and I hope to hear from you. I hope folks have some questions, and I hope folks have tons of ideas about how they can build great things on top of this. Thank you.